Let me scroll to today. Okay. So here's the code for today. I checked yesterday. It looked like homework 3.1 was graded, but 3.2 was still being graded. How did homework 3.3 go? Because I imagine that one really did. You had to scratch your noggin a little bit on that one. So did that one go well? Like it was one of those, like the calcs weren't hard, but maybe wrapping your head around what it was asking took a little bit of thought. So hopefully that was pretty straightforward. Okay. I would say that today's topic is one that is not hard to do from a computation standpoint, but it maybe is a little hard to wrap your head around. And that is moments about an arbitrary axis. Okay? But in order to do that, we are going to need to investigate dot products. Bless you. I am going to do a derivation, but I'm not going to do it on the board because how many of you have computed a dot product before? Pretty easy, isn't it? So I'm going to go through the same type of derivation, but the end result of that derivation is that the computation of a dot product is really easy. So I'm going to do it, but I'm going to go do it fast. Okay. Everybody got this? The code? Okay. So like I said, today's lecture might be a little difficult to wrap your head around, but I'll do my best to sort of simplify what's going on and why it's relevant. Just to make sure, we are still going to deal with cross products today and how we do them. So again, we'll probably be using cofactor expansion more, at least in our in-class examples, but I wanted to have that just that out there. The big thing I wanted to point out is remember that the magnitude of the cross product is the area of that parallelogram. And we can define the area of that parallelogram in relation to the cross product by saying the magnitude of these two vectors times the sine of that angle. And that's relevant because for the dot product, we're going to use the cosine of that angle. So, remember when we formally define a moment, what we're defining is the cross product of R and F. R being that position vector that starts about the point of interest and then ends on the line of action or the line of action that the force is acting on. And we can also compute that as F times D. Okay, so today's topic is going to be about determining moments about an arbitrary axis. But before I get into that, what I'll tell you is that in order to be able to do that, you have to be able to compute a dot product. So let's talk about dot products, okay? Now, computing a dot product is really easy. So let's go through a couple things. Remember that we have a formula for moments. So right now I want to talk about the motivation. We have a formula for moments in 2D, right? Now, technically, a moment in 2D is a vector, right? So if I have a vector, a force vector and an r vector along the xy plane, and I do the cross product, I get a vector along the z-axis, right? So a moment is a vector, but we also recognize that in 2 dimensions, because we always know the vector points along the z-axis, we recognize that the scalar magnitude is really all that matters, right? So even though moments are vectors, in 2D we were able to idealize that and just look at the scalar magnitude. So keep in mind that moments in 2 dimensions always rotate about the z-axis. What about moments about an arbitrary axis? Well, I propose moments about an arbitrary axis are also going to be a scalar term. And so that's why we're going to introduce a scalar product of vectors, or a dot product. Okay? Now, let's just go through how we're going to do this. So remember, when we did a cross product, the way that we derived it is we said, well, what's our goal? Our goal is a magnitude and a direction. And we defined the goal for the cross product such that we would get the same magnitude and the same direction if we multiply the 2 same vectors. Now for a dot product, maybe the static scared him or something. I don't know. That was a joke, not a very funny one. Okay, for dot products, we only need to define a magnitude, okay? And I propose that what we should do to define a unique magnitude is let's take the magnitude of P times the magnitude of Q times the cosine of the angle between the vectors. So if for the cross product it was PQ times the sine, let's say the magnitude of the dot product should be PQ times the cosine, okay? Just so that we get a unique product every time that we do it, that we dot vector P and vector Q, okay? Does that make sense? Now, remember how we went through the derivation of a cross product? We said, let's see if we can wrap our head around how to do the cross products involving I, J, and K. If we can wrap our head around that, then we can wrap our head around how to do the cross product of any vector, because any vector is a little bit of I, a little bit of J, and a little bit of K. So we're going to do the same thing here, okay? So if we look at dot products involving I, J, and K, okay, so they're actually really, really easy, okay? Remember, if we have a 90-degree angle, the cosine of that angle is 0, or is 90, or the cosine of a 90-degree angle is 0, but the cosine of a 0-degree angle is 1. Make sense? Okay? Here's why that's relevant. If I have two opposing vectors, like I and K, or K and J, or J and I, any two different vectors where the letters aren't the same, there's going to be a 90-degree angle formed between them, okay? And the cosine of 90 degrees is 0. So I propose that if the cross, or if the dot product has to equal this times the cosine, then any time that the letters are different, the dot product is 0. But if any time the letters are the same, like I dot I, or K dot K, or J dot J, the angle between J and J is 0. So the dot product of I dot I, J dot J, K dot K is 1. Anytime you're dotting a vector, a unit vector, like an I vector, or a J vector, or a K vector with itself, the result is 1. Anytime you're dotting it with one of its, alternates, the value is 0, okay? So if we go through and do this exercise like we did last time, remember how we expanded the whole thing into 9 terms? Remember we did that on the board? Well, anytime that the vectors are different terms, you get a 0. Anytime that they're aligned, you get 1. And so we get a pretty simple formula for the cross product. It should just be P dot Q is PX QX plus PY QY plus PZ QZ. And that's it. That's the dot product, right? And I imagine every one of you that's done a dot product, that's been how you've done it, am I right? Pretty easy. Dot product's probably the easiest, one of the easiest mathematical computations you'll ever have to do in engineering. Okay. Is everybody okay with this? Excuse me. So far so good? Now, for any mathematical operation, if we're going to define it, there better be a reason for it. Okay, so what are the reasons for the dot product? Where could we use it? Okay, well, one way we could use it is to compute the angle between two vectors. Like if you have two vectors in space, if you take P dot Q and then the magnitude of P and the magnitude of Q, you can compute the angle between them by dividing and taking the inverse cosine. So if you're ever given a math question like how to find the angle between two vectors, that's a really easy way of doing it. Okay. Another way of doing it is to calculate the volume of a parallelepiped. So rarely get to use that word in a sentence. But if I have three vectors, a prism or parallelepiped can be formed between them. And if I take the cross product of P and Q and then dot it with S, I can get the volume. But what's relevant to us in this class is the projection of a vector on an axis. Okay? In other words, that if I have, let's say, vector P, okay, some vector out in space, and I want to figure out how much of that vector is going to be projected onto a line. If I have a vector that defines this line, if I dot P with the unit vector for that line, I'm going to get that projection. Okay? Now that is a mouthful, but I'm going to explain why that's relevant right here. Okay. So let me get a marker here. write a moment vector here on the board. Let's write a moment vector. I just made this up. Everybody would agree this is a relevant definition of a moment vector, right? Right? I mean, we've seen these before. But what does this mean? Like, okay, 200 out of 300j negative 400k, but okay, like, what am I supposed to do with that? What is the meaning? Like, what does it actually mean? Okay, so let's do some 3D imaging. Okay, so let's take this point right here on the floor, and let's say that's the origin. Okay, so let's say that this is the x-axis. Let's say this is the y-axis. So x, y, and then z goes up like this. Okay, everybody with me on that? So x-axis goes this way. Okay, so the 200. What does the 200 mean? Okay, the 200 means the tendency to rotate about the x-axis, right? And I propose that that tendency is described by 200 Newton meters, right? That's the torque, as it were, right? And so what's the direction? Right-hand rule. My thumb points along the x-axis. So this moment vector is saying I want to rotate about the x-axis about that much in that direction, an amount of 200 Newton meters, right? So this vector says I want to rotate 200 Newton meters this way, 300 Newton meters this way, and instead of 400 Newton meters this way, it's going to be 400 Newton meters that way. Why is it backwards? Because it's negative, okay? So what this vector is representing is the tendency to rotate about the x, y, and z axis. That's what these scalars represent, the 200, 300, and 400, right? What I am asking for today's lecture is not how much do I want to rotate about x, about y, and about z. I want to know how much I want to rotate about this axis, pointing this way, some random arbitrary axis, okay? And I propose that the way that you do that is you take this vector and you dot it with the direction vector for that axis, okay? So a very reasonable question to ask at this point is, Dr. Mike, who cares? Who would care a hill of beans about how much a vector would want to rotate about some arbitrary axis out in space? Who would care? Okay? I'm going to give you a very simple reason why you should care. And the reason you should care is torsion. Okay? So, imagine you have a system where you have some sort of shaft out in space, right? And you have a force like this, right? That force might want to cause that to twist, okay? And so what we're trying to do is isolate how much twisting that element is to withstand so that later we can figure out, does it need to be made out of aluminum or brass? What's the diameter need to be? How thick does the wall need to be so that it can safely resist that torsion? But in order to be able to do that, we have to isolate, I've got this moment in 3D, how much is acting about that element. Bless you. Does that make sense? So that's why we're doing it, okay? So we're not doing it just because there is a reason, okay? Does that make sense? So what we're going to do is we're going to determine this mixed product or this scalar product by taking a moment vector and dotting it with this lambda, and the lambda is going to be about the axis in question. And again, why are we interested? Imagine you have a force out in space, you have a shaft or some element, how much is it twisting? Okay? So in order to do this, we are going to have maybe some slightly different definitions. So R is going to be about a point about which moments are taken, and it ends on any line of action of F. This term lambda, so in order to actually define lambda, lambda is going to start anywhere along the axis of that member, and it's going to end anywhere along the line of action of F. So I'll go ahead and tell you, my TA is going to have a very difficult time grading this homework because there's multiple different ways of doing it, and they can all be right. And you're going to see what I mean when we go through this example today. And by the way, you could do if you wanted, you could do the cross product and then the dot product, or you could do it all like this. You could just do one big old determinant and that would work. Either way is fine, and don't worry, we're going to get into an example of that right now. Okay, so let me pull up the notebook and sort of explain what's going on here. Okay, so, excuse me. So I've got a frame, okay, that is hinged here. It's got a hinge here at B, and so there's a cable going like that. This is the frame. There's a load here, okay, and I've got a tensile force in this cable, okay. So think about what's going on. There's a load here, and it's generating a tension in this cable. Now I know that the tensile force is 450 newtons. Okay, so the idea is that there is, let's just sort of draw that out, like right here, let's just sort of assume that there is a tensile force right there, we'll call it BH, and the magnitude is 450 newtons, okay? Now I propose that 450 newtons, imagine there's a shaft between A and D, that 450 newtons is going to want to twist that shaft a little bit, okay? I want to figure out how much twisting, how much moment is about this line right here, okay? So what we're going to need to do is we're going to need to figure out also this lambda vector in that direction, okay? So I'm going to call that lambda vector AD. Okay. So don't worry. We're going to take this one step at a time. One of the things that I did not point out is R. I'm going to get to R here in a bit, okay? Because there's a couple different definitions for R, and they would all work, okay? So for now, just recognize that lambda is the unit vector along this axis, and this is our force vector. So so what we're going to have to do is we're going to do lambda dotted with a cross product, and the cross product is going to be R and that. That's our goal. So we're going to need to define each of these vectors one at a time. Okay? Does that make sense? Again, like I said, this is probably the most difficult, like, 3D lecture that we have in here. Okay. So in order to do this, first thing I'm going to do is develop some point coordinates. Okay? Because I'm going to use these. And we can do a ton of these, but I'm just going to list the ones. I'm being a little precognitive, I guess I should say, because I know that these are the ones I'm going to need. Okay? So point A, point B, point D, and point H. These are the ones I'm going to need. Can somebody help me out? What is the coordinates of point A? Anybody know what that is? So keep in mind, that's the x-axis, this is the y-axis, this is the z-axis, and that's 0. Or sorry, 0. That's the origin. So what are the coordinates of A? That's right, 0, 0, and 0.75. Does everybody see that? Everybody see that? Okay, somebody else, what about B?
0.75.
Exactly right. All right, what about D?
How did you say the axis was again? Is Z or
X, Y, and Z. So what's D going to be? All right, is it, you're right on the Y and Z, but is it 0.75 or along the x-axis?
It's
1. Okay. And H is going to be what? Along the X, 0.875. See that? That's this dimension right here. Along X, along Y is going to be,
0.75.
and then along Z, there you go. Does that make sense? Everybody okay with that? Okay. Okay. Now, in order to compute the moments about this axis, which is what we're trying to do, we're trying to compute the moments about axis AD, we need to figure out lambda AD, okay? So in order to do that, we need, so how do we, tell me, how are we going to get lambda AD? How, like, just walk me through conceptually how we're going to do that.
The direction vector and then find the magnitude and then divide the direction by the magnitude to get the unit.
100% right, yeah. So we're going to get, so the idea is this. So the idea is, okay, to get lambda AD, we're going to take AD divided by the magnitude of AD. That's what we're going to do, right? That's our method. So how do we get AD? We say, all right, we have the coordinates of D and the coordinates of A. Negative. Sorry. So AD is that, right? And again, I know, like, you might not write the 1, or you might not even write that. I'm just writing all the terms just so you see where I'm coming up with all this. So I'm sure there's some math professors like, you'll need to write all that. I know. I just want you to know where all the values came from. Okay? So tell me what to do.
take the magnitude.
Take the magnitude. So the magnitude of AD is and what do we get here?
1.25.
1.25. This is really just a 3, 4, 5 triangle, just sort of hidden in 3D, I guess. Okay. So we could say that this vector right here we could do that, right? That a fair statement?
Yeah.
Okay. So now what I'm going to do, I'm going to skip the r vector. I'm going to do the force vector next. But before I move on, does anybody have any questions? Am I going too fast? Is this straightforward? Everybody good? Okay. So now let's do the force vector. And that's going to be along line BH. And remember, this is, what is it, 450 newtons?
Yeah.
Okay. Now remind me, how do we do a 3D force vector? How do we do that? We take the magnitude times what? Remember, we do the lambda? Because remember, all this is just a force vector. Is that times that? Remember that? Okay. So, and how do we get a lambda vector? We take the distance vector, divide it by its own magnitude, right? So, same idea, okay? So, can I scroll a little bit? Everybody good? So, again, it's just kind of the same idea, all right? So, BH is, we take H and B and we subtract them. H is 0.875, 0.75, and 0. This is 0.5, 0, and 0.75. Right? So if I subtract these, I get that, that, that. So BH and what are the units for that? Making sure everybody's paying attention.
Is it meters?
Meters. This is a distance vector. Next step is to compute the magnitude of this vector, right? Divide by its own magnitude. So and I'll go ahead and do this one for you. This one ends up being 1.125 meters. And then, so when you compute lambda BH, you get You get that. And that divided by that is going to be, what, a third? This is 2/3, that's 2/3, right? So we're going to get that, right? So what do I have left to do?
Multiply it by the force.
By the force. So, because again, this is a distance vector. This vector is unitless. So I think I can do that one in my head, because a third of 450 is 150, and that's going to be 300. So we're going to get 150i and that is in newtons. So just to sort of note that on the board. Okay. Okay. Let me take a step back, because we've done a lot of chugging out some numbers. I want to make sure that what we've done so far makes sense. Okay, is everybody with me so far? Any questions? Okay, so here's where things get interesting. Okay? Okay? Up until now, we've been taking moments about a point, but we're not really doing that. Now we're taking moments about an axis. Okay? So I'm going to refine my, my definition a little bit. Okay? R is going to start anywhere along the axis in question. Okay? In other words, anywhere along the axis defined by that line. Okay? And it's also going to end anywhere along, and this one you can probably guess, the line of anywhere along the line of action of the force. In this case, TBH. So I propose there's actually, so this is where things are actually going to get a little challenging for me and the TA in terms of grading. There's actually, I see 4 different options. Like, we could go from point D to point H. We could go from point D to point B. We could go from point A to point H, or point A to point B. I propose we'll get the same answer with any one of them. And we're going to do one, and then I'm going to show you another one that would be easier, but just bear with me. So we're going to do the problem a little inefficiently, and then I'll show you how another way of doing it would be a lot more efficient. And I think that there's value there, because it might make your homework a little easier. So let's just try R let's try R from D to H. Again, it's got to start here and end here. Okay? So if I want to find the distance vector from D to H, I take point H and point D and I subtract them. Okay? Point H was 0.875, 0.75, 0, and this is 1, 0, 0. Okay. So, let's see, 0.875 minus 1, that's negative 0.125, 0.75, and 0. I propose that we could use R as this. By the way, what are the units of that going to be? Meters. So this is an option. So we have a lambda vector with no units. We have an R vector in meters and a force vector in newtons. So what's the answer going to be? Meters, newtons, or newton meters, right? Because it's still a moment, right? We are still calculating a moment. Okay, in this case, it's the moment about AD. So it should still be in newton meters. Okay. Now, if we want to find the moment about that axis, so, I mean, how are we going to find that? It is this. Okay? Now, I want to be clear. If you can do R cross F and get an answer, you could dot it with that, and that'll work. By the way, I have a typo because that's not a vector. That's going to be a number. Okay? Whoops. That's just M, not M with an arrow. Okay? One way of doing this calculation is to say, I did it again. One way of doing it is to just do the whole thing in one fell swoop. So 0.8, 0, 0.6, is to do it like that. Okay? And how do we do this? We do it the same way that we did the other ones. Okay? Just instead of I, J, and K, just use 0.8, 0, and negative 0.6. So 0.8, 0, and then 0.6. Now I'm making that negative because In the IJK, this is positive, but that's a negative value. Okay, hold on. This is getting a little squunched, so I'm going to move that down. Okay, so that is one way of doing it. Okay. Now, is everybody okay if I just give you the answer? Like, because I have, does everybody feel comfortable with doing this calculation? All right. I propose that the answer to this is negative 90, or specifically, negative 90 Newton meters. So, yes?
Should the final 300, it's 0.6 times, should it be positive?
Oh, that should, yes. Yes, you're right. That's 0.300, or 0.75. Yes, you're right. Thank you. Yeah, hold on. Let's see. Yep. And then, yep. And then, yep. Okay. All right. So I propose that this is the answer. Okay. So MAD okay. Now, if you had to chug this out in a calculator, what magic number in these computations makes it so much easier? 0, right? For example, do I have to do this one at all? So maybe if I had an R vector with a bunch of zeros in it, it would make my life a whole lot easier, right? Okay. Remember how I said that there's multiple different R vectors that you could use? Okay. So I propose that there are 4 different R vectors that you could use. You could use AB, you could use AH, you could use DB, and DH. That's the one we used. We used D and H, right? That's the one we used. Okay? What about AB? Let me show you something. I'll say note other R vectors work. And R from B to A, or AB, if you compute that, is that this is 0.5, that's 0, and that's 0. And so if you wanted to do this calculation, replace this row with 0.500, you would get the same answer. But you'd have more zeros, so it'd make the math a little easier, right? And so here's a way of identifying that. If you go up to the sketch, all right? So from here to here, right? Along the line of, so from the line of action to the force, that just goes along the same axis. So the z value is 0 and the y value is 0, so it's only x, right? So you're being able to use a vector that's really, really easy, okay? So what's going to make the homework a little challenging to grade is that just like this problem, there's 4 different R vectors, and they could all be right. So, but that's our challenge. We got to deal with that. Okay. Let me take a step back. Does anybody have any questions? And I guess, does anybody have any questions about the exam? Again, I think everybody did fantastic. So grades are recorded on that on Blackboard, so sound good? All right, you're getting 3 minutes of your life back. I'm going to pull the code up one more time. I will see you all on Friday.